Welcome to this movie on statistical mechanics, which deals with the Gaussian model. My name is Jos Thijssen and I teach statistical mechanics to applied physics students at the Delft University of Technology in the Netherlands. The Gaussian model is a very important model because it acts as a reference model for renormalizing the Landau-Ginzburg Hamiltonian, and that will be the subject of another movie. In fact, within the Gaussian model you can perform a renormalization transformation rather easily, and that takes place in reciprocal space, so it's in that sense a different approach than the real space renormalization, on which I have made another movie. And this movie is very important to really understand well before you go into Wilson renormalization of the full Landau-Ginzburg Wilson Hamiltonian. I hope that this movie is instructive for people wanting to learn about phase transitions. The Landau-Ginzburg Hamiltonian is the standard Hamiltonian to study systems close to a phase transition. I've written here the simplest version, which is expressed in terms of an order parameter, which is in this case x. It's a one-dimensional order parameter. It's the simplest version. There is first a fluctuation term, which gives a penalty for variations in x. And then there are two terms forming either a double or a single well. And then there is a magnetic field. So if there is a double well, then one of the wells will be favored above the other when there is a non-zero magnetic field in the model. In order to calculate the critical exponents for a system described by this Hamiltonian, we need to carry out a renormalization procedure. And that is very complicated for the model as a whole, and therefore we simplify the model a little bit by first taking the u and h to be 0. So we set u equals h equals 0. We arrive then at this form of the Hamiltonian, which is a lot simpler. It's defined in terms of the order parameter x, which is real, and we have an arbitrary dimension of the space in which our system is defined. The Gaussian model can also be viewed as a physical model for a surface. Here I've drawn a cartoon for a one-dimensional surface. And assuming that a flat surface has the lowest energy, we need to pay an energy penalty for each of the height differences that you see here. So all these heights, they cost energy because they imply deviations from a flat surface. Although physically we would be tempted to take an energy penalty here which is perpendicular to the length of the difference, so that's the absolute value of the height differences. We can also assume that it's a quadratic function of those height differences, and then we arrive at a Gaussian Hamiltonian, although in this case the heights xi and xj, they are discrete. They do not assume any real value. For high enough temperatures, however, the height differences are usually a lot more than 1, and so in that case the actual discreteness doesn't influence the behavior of the model. It becomes irrelevant and we can neglect it. So at high enough temperatures, whatever that may be, the xi can be taken continuous, and then it will give still a good description of this roughening model. Here is the Hamiltonian once again. It's important to note that the I and j lie on a d-dimensional grid, d-dimensional lattice, and the xi and the xj, they are continuous variables and they run from -infinity to +infinity. And to make progress, it's convenient to take the Fourier Transform of x with respect to the index I. So xi can be written as a sum over q of the xq's with the well-known Fourier factor, and this is the inverse transformation. And because x is a real parameter, if we take the Fourier transform of x at -q, we see that we get an e to the power plus iq ri, and that's precisely the complex conjugate of xq. So x minus q is x complex conjugate of xq, and that is typical for a real field. Now we will introduce that Fourier transform in the two-dimensional version of the Gaussian model, in which every I couples to the side which is at the right neighbor, that's I plus ex, that's the unit vector along the x direction, and there is also a coupling along the y direction, so that's here. Let's work out one term in some detail, that's the term xi squared. We then replace each of these xi by the Fourier transforms. One has a variable q over which we have to sum, and the other one a variable q primed. And then we use the well-known fact that sum over I e to the power I q dot ri summed over ri gives you an n times a delta function for the q0. It says that if q is not 0, then this phase factor will average out when you sum over the ri. So it singles out only the q being 0. And if we then consider this expression, which contains an e to the power I q ri and an iq primed dot ri, and we sum over the ri's, then we see that the q plus q primed must be 0. In other words, q must be minus q primed. And if we then implement that condition in this expression here, we find that the sum over I xi squared is given as a sum over q of xq times x minus q. We can perform a similar calculation for the terms xi times xi plus ex summed over all sides I, and then we find a sum over q xq x minus q e to the power minus iqx. And so we can perform this kind of calculations for all the terms arising in this expression. If we work out the squares, we have a lot of terms, and we will not do, of course, all the steps in detail, but we merely give the result, and that is the following. We obtain the form beta h is j over 2, sum over q xq x minus q, and then the factor 4 minus 2 cosine qx minus 2 times cosine qy. In the end, we shall be interested primarily in the long-range behavior, where the q is small, and so we can perform a Taylor expansion for the two cosines. These Taylor expansions are respectively 1 minus qx squared over 2 and 1 minus qy squared over 2, and if we plug that in, it turns out that we find j over 2 sum of q x minus q times q squared. We have already emphasized that the real space positions of the x degrees of freedom lie on a d-dimensional grid, and in 2 dimensions we have therefore that q is bounded to a Brillouin zone which runs from minus pi to pi, both for the qx and for the qy, and so here you have the cartoon of the corresponding Brillouin zone. Here I've copied the Hamiltonian at which we arrived, and I note that previously we had a Hamiltonian which had this particular form, so they are very close. The gradient here translates into a q, and so then this term has the same form as that term, except for the fact that there is a j here and there is an additional term r0. So we need to analyze in how these models are related. First of all, the prefactor of the gradient term, and then the meaning of this term. Let us start with the second issue, the meaning of this term. It gives us a penalty for x being different from 0. Where in terms of this surface that we have studied as a background for the Gaussian model, it means that there is somewhere a level, which I call the level x is 0, and that's where the surface wants to be. And if we have deviations from that, we pay an extra penalty because we are not at x is 0. In order to address the prefactor of the gradient term, we look at the partition function. We consider the partition function, which is a sum over all the xq variables running from minus infinity to plus infinity. We have to take all the xq variables where q is inside the Brillouin zone, and here I have added this R0 term to the formulation of the model in terms of the q. You could argue that I should put a sum over q here, but that's taken care of by this product over q. That product also acts on all the exponentials that you see here. Let's now see what happens to this partition function if we replace the xq by lambda times xq. So we just rescale our x variables. Obviously this rescaling shouldn't do a lot because I have to integrate over xq running from minus infinity to plus infinity. So we get two contributions from this rescaling. The first one is a Jacobian term which comes from the integration variables, and the second one occurs in the interaction, and it should be of course the same partition function that we have now than the one we had there. We have properly taken into account the Jacobian. Now this Jacobian is just a prefactor to this z lambda, and it will drop out whenever we calculate an expectation value, because then we will have such a term in the numerator and in the denominator. And so this term is really not relevant. It will not affect the physics of the problem. So it turns out that this Hamiltonian here is somehow equivalent to the Hamiltonian that we have there. There is only a trivial factor which doesn't affect the physics in the partition function, which is the only difference. So we see that although the Hamiltonian still describes the same system, it has renormalized parameters, it has rescaled parameters. The q squared is replaced by lambda squared times q squared, and r0 by lambda squared r0. But the Hamiltonian is essentially the same. And therefore we can always choose a lambda such that a prefactor of this q squared is 1/2 or minus 1/2 if you want. It's 1/2, and whenever we find another value, another prefactor before this q squared, we can choose a rescaling with a lambda such that we gauge this term, we calibrate it to be 1/2. So that means that the Gaussian model has only one parameter, and that's the R0. So that's very important to realize this. There is only one relevant parameter which describes the physics of the Gaussian model, and that's this R0. The other prefactor of the q squared is always being put equal to 1/2. So it is this Hamiltonian that we will study from now on. It always has the same prefactor of the q, 1/2, and the only relevant parameter of the model is the R0. And it's also very important to realize that the q's, so the qx and the qy in 2 dimensions and qz in 3 dimensions, etc., they are always inside the interval running from minus pi to pi. And the fact that they do this tells you that the lattice constant is equal to 1, because this is typically minus pi over a to plus pi over a for a lattice constant a. And we fixed the lattice constant rigorously to 1. So that's also part of the definition of the model. So this tells us that the lattice constant is 1. Now a very important thing to note is that in this Hamiltonian, this term in the summand is symmetric under q replacing q by minus q. So if we reverse the q's, then this term doesn't change at all, because there is an xq and there is an x minus q, and the q squared obviously is insensitive to this operation. So if we want to calculate the partition function, that can be done in a rather convenient way by integrating over dxq, dx minus q. But if we would take q in the entire Brillouin zone, then we would have, for example, once a q here, and there would be a minus q here, And in fact, in that case, I would have this pair occurring twice, which doesn't make sense because each xq should occur only once. Therefore, I split the Brillouin zone into two parts. One part is the right part, so that's the part with qx greater than 0. And then we have here, of course, an ambiguous axis, that's qx is 0. And I deal with that axis by just taking this line into account, but not the lower part. And then there is a separate point, and that's the origin, because q is 0. For that point we do not have this symmetry, so I should count that only once. So in this product over all the q's, I should take the q's only in the blue part, and for q is 0 I should count that only once. To emphasize this point, let's go back to the Hamiltonian. In this case I count every term twice because I sum here over the entire Brillouin zone, and the points with q and minus q, they give us the same contribution, but there's no problem with that. However, if I do an integral and I need to integrate over a variable, I should have one integral over each independent variable, and that should not occur twice. So in this case I should write the partition function as follows. I have first an integral over the dx0, and that occurs with an ordinary Gaussian integral, and there is the factor 1/2 which occurred in my Hamiltonian. And then I take the product over all the q's in the blue Brillouin zone. That's only this right half, and I call that the bz plus. So the bz plus is only the blue half of the Brillouin zone. Then I have here a dxq and a dx minus q. They are independent variables, so I should integrate over both of them. And now in the numerator, because this product over the q and the bz plus implies a sum over the q only in the bz plus, I do no longer have the factor 1/2 here, because now I count every term with 1q only once. Only the right half of the Brillouin zone, and that's why I don't have any longer the factor 1/2 in front of my Hamiltonian. I have half of the terms, and therefore I multiply them by a factor of 2. To calculate the second part of this integral, for each q, we use the notation that small xq can be written as capital XQ plus I times capital YQ, where the big X and Y, the uppercases, they are real, and so I can transform then from the integral over little xq and its complex conjugate to the real part and the imaginary part of x, and that's just a two-dimensional integral. This integrand will give me an xq squared plus yq squared, this product over the xq and x minus q. And so we have a two-dimensional Gaussian integral, which is easy to do. If I call xq squared plus yq squared rq, so we are using polar coordinates, then I can write this integral completely in terms of polar coordinates, 2 pi for the angle, and then we have an rq drq, and then this term in the numerator, and this is an integral that you can do right away. The result then is first a term which derives from the integral over the dx0, and that's a Gaussian integral. It gives me 2 pi over r0. And the second one is this Gaussian integral multiplied by rq, which makes it a lot easier. And we find for that 2 pi divided by r0 plus q squared for each q in the blue part of the Brillouin zone, the bz plus. If I then want to restore the q to lie in the entire Brillouin zone in the product, I need to include an extra exponent of 1/2, because each term here occurs now twice here, and I compensate for that with the 1/2. For the 0 I don't need to do that, but there is already a factor of 1/2, so this is the correct partition function. And obviously in the end we are interested in the logarithm of that partition function. That will give me something like a free energy, and that gives me then a integral over the entire Brillouin zone of d dq. In fact, we have only used 2 dimensions as an example, but obviously this result holds for any dimension. And then we have this term in the integral. Apart from the partition function, it's also interesting to consider the correlation functions, and in the Q space they read it's just the expectation value of xq1 and xq2, where q1 and q2 are vectors in the Brillouin zone. And I will not prove this extensively by a calculation. It all proceeds along the same lines as the calculation of the partition function. The result is that it's 1 over q squared plus r0 times the delta function q1 plus q2. Well, to argue that indeed there is a delta function of the q1 and the q2, if the q1 and the q2 are different, if you look at the weight factor, that occurs in calculating the expectation values, you see that it factorizes into a product for each q. So if I have only one xq for a particular q, then because of antisymmetry, the integral over xq will vanish. Also, if I take xq in the argument, that would be of course still a possibility to have a combination of 2 of the same q's, but then it turns out if you evaluate this gives you the real part of xq minus the imaginary part of xq squared, and so these 2 expectation values are identical and they vanish. So this is the correct expression for the correlation function of the Gaussian model formulated in reciprocal space. So what then about the correlation functions in real space? We can calculate those from the Fourier transforms. So if we take xr times xr primed and want to know the expectation value, so the r and the r primed are positions. Previously we called those I and j, but here I want to have a more natural notation in view of the Fourier transform. And we write the xr as a Fourier transform. We also write the xr primed as a Fourier transform, one with the vector q and the other one with the vector q primed. And we know this guy, which gives you a delta function, and the result is that we find 1 over q squared plus r0 times this. Now we have encountered already this Fourier transform when we were looking into the Landau-Ginzburg theory, especially when we were considering the correlation function for that. And we know therefore from that analysis that the correlation function has the following form. That is, we know the correlation function for large separations. For that case, we can make the approximation that q squared is much smaller than the r0, and an asymptotic solution is then formulated as follows. It's first a power law. It's r to some power in which the dimension occurs, and then it's screened by an exponential decay. And the decay length, that's the correlation length, xi, and we see that xi scales with r0 to the power minus nu. And that's the definition of the critical exponent nu, and therefore that's r0 to the power minus 1/2, and we find that nu is 1/2 from this analysis. And recall from the Landau-Ginzburg theory that the parameter r0 vanishes at the critical point, and it's linear when we are close to the critical point with the temperature difference. So now we start with the main course of the movie, and that's the renormalization of the Gaussian model. And I have repeated here the beta h, the Hamiltonian, which is formulated in this way. And sometimes if you want to work with only unique q points, only in the bz plus, we no longer have the factor of 1/2, because here we sum over only half the points. So those are 2 alternative formulations of the same model, where you should, however, always take a little bit of care about the point q is 0. Also, it is very important to realize that the model only contains one parameter r0, because we have seen that rescaling of the x's can always be used in order to fix the prefactor of the q squared term to 1/2. And furthermore, there is a lattice constant, and the lattice constant is not directly visible from this formulation, but it's hidden in the shape of the Brillouin zone, and the Brillouin zone runs from -q to minus pi to plus pi, and that corresponds to a lattice constant of 1. So the lattice constant A is 1. So A is the lattice constant. So we need to perform a renormalization, and because the Gaussian model has a simple formulation in Q space, we perform the renormalization also in Q space. And the question then arises, how should you do that? Because the renormalization theory is more intuitively applied in real space than in Q space. Nevertheless, there is a recipe for doing this, and in fact the original renormalization by Wilson was all based on renormalization in Q space, and this recipe makes as much sense as the recipe that we have for real space renormalization. Here is the recipe. The first step consists of integrating out all the fast degrees of freedom. What are the fast degrees of freedom? Those are the ones that vary with a short wavelength. It means that they vary with a large q. So we want to integrate out all the x's with a large q. Now the q, the maximum value of q, is pi. And therefore we now take a segment of the Brillouin zone between pi over b to pi. Note that b is larger than 1, so this is a smaller q than the upper boundary. And we integrate all the xq's with q's lying between those boundaries. Here you see a cartoon of the Brillouin zone, and it's this segment here over which we integrate. We take all the x's with q's in this segment and we integrate them out. And so then we are left with the slow degrees of freedom, the slowly varying xq. But of course, we need to get back to the original Hamiltonian, to a Hamiltonian which has the same form as the original one. Now the original one was defined on a Brillouin zone which ran from minus pi to plus pi for each of the Cartesian directions, and so we want to have the new Hamiltonian to have the same property, and therefore we rescale now the q's to bq so that the upper limit is restored and is again pi. Then there is a final step. When we do this, when we rescale the q, then we anticipate that this term here q will get a different prefactor because it's rescaled. And we want to restore the prefactor of 1/2, and we have seen already how to do that. We rescale the xq, just the integration variable, which doesn't change the physics of the model. So we introduce then a new integration variable x tilde, and that causes us to restore the prefactor 1, and so that's the prefactor apart from the 1/2. So here is the 1. That is restored by this transformation. So we have 3 steps in summary. We integrate over the fast degrees of freedom. Those are the xq's that live in this part of the Brillouin zone. And then we increase the size of the smaller block here, which contains the fast degrees of freedom. We rescale it to fill again the original Brillouin zone. And then we restore the factor of 1 in front of the q squared by a simple rescaling of my integration variables. So that's completely different rescaling as the rescaling of the q, obviously. It's just there to restore this prefactor. So let's get down to business. Step 1, we integrate over all the xq's where q lies in this blue part of the Brillouin zone. So those are the large values of q. I integrate over the xq. I should of course take care about the symmetry of the integrand. I have neglected that here because I had a factor of 1/2, but in fact when you do this you may argue that you do it only for the part in the bz plus and not in the entire bz. But we will neglect those kind of subtleties because they are not relevant for the analysis. Now it may seem at first sight that this is a difficult thing to do, but it's not, because an integral over these variables, that we carry that out already when we calculated the partition function, and it's just the other xq's over which we do not integrate. They are just still there, and the Hamiltonian for them still has the same form. So this leaves us with a Hamiltonian of the same form, but now the qi's lie between 0 and pi over b. Alright, so I have just integrated over these xq's. That gives me a number, a prefactor, which is not relevant for the Hamiltonian. And everything which is left in the Hamiltonian are the q's that are inside this, small q part of the Brillouin zone. So those are the slow waves of excitations. And the Hamiltonian for those slow degrees of freedom is still unchanged. Realize, by the way, that this operation leaves us with qi's being smaller than pi over b, and so b is now recognized as being the new lattice constant of the model. So we have rescaled the lattice constant from 1 to b. Step 2 is then to rescale the new lattice constant b back to 1. And in reciprocal space this means that the old q's are rescaled. We multiply them by b and we get new q's that fill up the original Brillouin zone. And so to be specific, the q primed is defined as b times q. Let's look at the h primed. That is the Hamiltonian that we got after step 1, which is exactly the same as the original Hamiltonian, except that the sum is now only over the qi, which were inside the small part of the Brillouin zone, so the part that we did not integrate over. And if we then rescale this q to qi primed, then we have the sum over the full Brillouin zone, but we see that we have to pay a price, because if we want now to express the Hamiltonian in terms of the new q primed, for the x it doesn't really matter, they get primed, but here we see that a q primed is scaled by a b in the denominator, a b squared to be specific. And we want, let me emphasize that, we want this prefactor for the q primed in this case to be 1/2 and not 1/2 divided by b squared. So we should get rid of the b squared. That is realized in step 3, which consists of restoring the q primed term prefactor, which is 1/2, by rescaling. So we introduce a new integration variable, x tilde q, which is related to the xq in the following way. The xq primed is now b times x tilde q primed. So we get a factor of b squared in front of this that eats this factor b squared in the denominator here, but it also adds an extra b squared with the r0. So we see we have a new value for the r0 after the renormalization procedure, which is r0 primed, and that is related to the old one by a factor of b squared. Apart from that, everything is still the same. I mean, the fact that the x tilde q has now, it looks a little bit different because it's an x tilde, but it doesn't really matter because it's an integration variable when we calculate the partition function. The fact that we use a q primed here, I should also put that here, it doesn't matter because q primed runs over the entire Brillouin zone. And so this Hamiltonian is the same as the original up to a change in the parameter r0, which is now b squared times r0. Now, if we look at this result from a renormalization theory standpoint, we see that r0 primed, which is the only parameter in the model, is b squared times r0. Now, according to the renormalization theory, that relation should be b to the power z, where z is the so-called scaling dimension, times r0. So this is the deviation from the critical temperature, this parameter r0. And we see immediately that the z must be 2. Now nu, from renormalization theory, is known to be 1 over z, and so we recall the value of nu is 1/2. So we find that the correlation length scales as t minus tc to the power minus 1/2. Now you may argue we have just obtained that result already, and that is true. That was in the context of a direct calculation of the correlation function. There we found also the same exponent. But here we have found that result from a renormalization transformation. And so it just gives us confidence that we have done this renormalization transformation correctly for the Gaussian model. We can also consider the renormalization flow, which looks rather simple. R0 is 0, so that's the critical point, so that's the same as t is tc. That's a fixed point, because when R0 is 0, it will remain 0. And if we move away from R0 is 0, then our deviation will be amplified by a factor of b squared. Recall that b is always greater than 1. Note that the model is only properly defined for R0 positive. In fact, if it would be negative, there would be a potential it could become arbitrarily negative. However, if there is also a u term present in the Hamiltonian, like in the Landau-Ginzburg theory, you also have a u times x to the power 4. That will again make the model acceptable, so even the trend for the renormalization for negative R0 is in that case still relevant. And that concludes the renormalization transformation of the Gaussian model.